Okay, let's get started. So I'm going to start a new topic today, which is the link layer. And actually, it's going to be for this lecture and the next two lectures. Good. So today I'll talk about the context of the link layer and what types of link layers there are and what services they provide. And the very important issue of multiple access, which means how do we share the link? How do we make sure that two people who want to access the link at the same time can share it? And then we'll talk about the most important wired link layer, which is Ethernet. And then next time, talk about Wi-Fi, which is also a very important multiple access type or link type. And then class after that, we'll talk about cell phones. And we'll talk not just about the link layer, but pretty much the whole cell phone architecture, which goes all the way to application layer as well. Okay, so let me just start with the context over here. We've already studied the application layer and applications like P2P applications and so on. And we looked at how TCP is a very common transport layer. In fact, it's the most widely used transport layer on the internet today. And below that, we have IP, which is your network layer. And we saw how at the network layer, we had to deal with issues like addressing and address aggregation, routing tables, and forwarding, and routing. So we looked at all those issues in the last several lectures. And now I'm going to look at the link layer. So the network layer is, if you remember, providing this ability to stitch together links to form an end-to-end path. So we started out by saying applications need an end-to-end sort of a pipe to talk to each other. And in fact, in your assignment, you actually implemented or used sockets to have clients and servers talk to each other. And as you probably realize, the client and the server that you had in your homework assignment could be anywhere. You could have your client in one end of the world, server at the other end of the world, and they'd still be able to talk to each other because you have this notion of an end-to-end pipe. And we saw that that pipe is not reliable. It has errors in it and so on. And that transport layer, by using sequence numbers and flow control, is able to provide this nice abstraction. You just send bits in, it comes out the other end. We saw that the network layer provides this abstraction of a path, okay, so that the transport layer doesn't need to worry about routing and things like that. And the link layer is now at the bottom level. All it allows you to do is that given a link, you can send some stuff on one side, comes out the other end. So it's relatively straightforward, which is why I can cover most of it in just a few lectures. Okay, so how does it actually work? The way it works is something like this. We typically have what we've been calling a host. Let's say it's a laptop or it's a mobile phone. Okay, so they have on them a piece of hardware. It's called the network interface card. And it is a piece of hardware that's either has a wired or a wireless connection. Let's look at the wired connection for now. And typically this would be wireless, but if you look at the wired connection, it's a wire that plugs into something, right? And that thing over there is the network interface card, and it's a piece of hardware. What this hardware does, it provides a link layer abstraction. So the software, the operating system, which is running on the CPU, can send an instruction to the network interface card saying, send something. What it sends on it is called a frame. Okay, and so the frame gets sent out and it goes into a switch, typically. And this switch has another network interface card, and as usual, we'll abbreviate that NIC, or NIC as we call it. And so that switch network interface card is talking to this switch interface card, and what they talk to each other are these frames, and this is what the link layer does, basically. The link layer is responsible for the communication that happens between these two NICs. It's basically as simple as that. Now the switch in turn will have multiple NICs, one per port. So if it has 4 ports, it will have one per port, and this will be talking to some other entity, and so on. And this, of course, could talk to a router. and the router in turn will have its own little NIC like so. And it's all NICs everywhere, basically. Okay. So all communication, at the end of the day, turns out to be between two network interface cards. Now, it could be wireless, in which case we have a wireless network interface card. Here's an access point, and that will have a wireless network interface card. And then you have wireless communication between the two, but it's still a network interface card. Okay? So we're going to focus really on what these network interface cards do, what these NICs do in the link layer. Okay. Any questions about this? Okay, so that was the first in this context we'll talk about. The NICs have a particularly important distinction between them, okay? And the main, really two types of NICs, and the two types are point-to-point and broadcast. And these are really very, very different, and I'll explain what it is in just a moment. A point-to-point NIC means that a frame that's sent on the NIC is received by exactly one other entity. And typically, if it's a bidirectional link, you'll actually have like 4 wires going through, so you can send in this direction and in this direction at the same time. Okay, and most NICs today are actually bidirectional. You can send and receive at the same time. And this kind of bidirectional point-to-point link is most commonly used in wide area links. So if you have a link that goes from Kitchener to Toronto, for example, which is it would be an optical fiber, and that's the physical layer. Okay, that optical fiber is it's actually thinner than a human hair, very, very thin, very, very pure glass. Okay, I think I mentioned this to you. The glass is so pure that that glass, if you had a window 1 kilometer thick with that glass material, you still wouldn't be able to see it. Light would go through without any distortion through a window 1 kilometer thick. That's how pure that glass is. Okay, super pure glass. At any rate, those kinds of links are point-to-point, and they're actually kind of boring, okay, because you send something, gets to the other side, and with optical fibers, there's practically no loss. It just goes through, and we receive almost everything, and the capacities are tremendous. Okay, we can send today on one optical fiber 40 billion bits a second, 40 gigabits a second. Okay, that's a lot of capacity per color, per laser. And if you want 10 lasers, you're talking about 400 gigabits per second, which is quite a bit. Okay, and you can actually even have higher capacities if you want. It's just that there's no need for it. It's just too much capacity. You just don't need it anymore. So those are kind of boring. The point-to-point links are boring, and all you really have to do over there is you send a packet or send a frame, the other side gets it, and you're done. Okay, so we won't really talk much about them at all. We'll focus instead on broadcast links, because these arise in many different contexts. And the two particularly important contexts are, first is the wireless link over here. So the wireless link is broadcast, meaning that if you have two cell phones that are both trying, or two devices both trying to talk to the same wireless access point, and they both speak at the same time, the receiver cannot distinguish between the two. It's exactly as if you're in a room and the two people speaking at the same time. And they're speaking at the same time, you can't hear them because they overlap. And if anybody overlaps, the receiver says, sorry, I can't make out what's going on. The noise level is too high, and in fact, both transmissions are lost. Okay, so it becomes extremely important to coordinate these transmissions so that only one is speaking at a particular moment in time. Okay, and that's what's called the multiple access problem. We'll come to that in a minute. Okay. So this, of course, is very different than here, because if you had a point-to-point link, no matter who was speaking, it's not a problem because you have a separate point-to-point link. So the broadcast arises naturally in the wireless case, right? Because it's a wireless system. The other place where broadcast shows up is in the case of hubs. And I haven't really talked much about hubs, but let me explain what it is. So unlike a switch or a router, a hub has no network interface card. Okay, it doesn't have a network interface card at all. So let's say you have two devices over here. Okay, and these are connected to the hub. What happens is that whenever a frame is put on the link by this NIC, let us say over here, it's received by all the others. So all of them are going to get a copy of it, and if there's many more, they'll all get copies of it. And so from the perspective of the NICs, it's as if it was broadcast. You can think of it as wired broadcast, which is exactly what it is. Okay, and we'll talk about Ethernet. You'll see what that means. How many people know what ether refers to? What is ether? The luminiferous ether, right? So the famous experiment by Michelson and Morley in the 1880s was to show that there did not appear to be an ether, okay? Because ether was what light went through. The idea was, what is light? If light is a wave, what is waving? What is it that's waving? Well, something is waving, because otherwise how could light be a wave, right? And so something had to be between the sun and the earth, otherwise it wouldn't be waving, and that was called the ether. And so that was the medium for electromagnetic signals. Now, unfortunately, ether is also what they put on your nose to knock you out when you go into a hospital, okay? And for a long time I was confused. I said, why is it that what knocks you out is also what carries electromagnetic waves? Okay. But unfortunately, it's not the same. What Ethernet does is to take the wireless medium, essentially broadcast wireless medium, and put it onto the wire. And that was the intuition that was that the inventor of Ethernet had. Okay, Bob Metcalf, who was a graduate student at Stanford, had worked in wireless networks. And I'll tell you the story in a bit. And he said, you know what, we could make the wireless medium and make it wired. It will still look the same. So he called it Ethernet. It was a joke. It was saying, I'm taking the luminiferous ether and I'm putting it into these bits of wires. Okay, and I'm going to call it Ethernet. That's why it's called Ethernet. So it actually refers back to the wave theory of light that goes back to 1670 in the whole fight between Huygens and Newton. But anyway, we won't get into that either. There's history behind everything. If you scratch it a little bit, you'll find there's a lot of history behind everything. Okay, so what we have here is these hubs, in Ethernet hubs in particular, are pretending to be wireless. And so we have broadcasts there. And so we have these broadcast medium arising both in wireless, Wi-Fi for example, and Ethernet hubs which simulate a broadcast medium. In both cases, we need to solve the multiple access problem. Why? Because if, for example, both of these were trying to talk to this guy at the same time, they both put a frame on at the same time, both of them would be received one on top of the other at that receiver, and they would both collide, and you would not be able to make them out. And so you'd have a collision, as they call it. And so you'd have exactly the same problem as if both of these were talking at the same time. Okay? So you want to make sure that only one person talks at the same time. Okay, so let's look into some of the services provided by these link types, the broadcast and the point-to-point. They both share these. And so here are some of the services, and I'll just explain what they are. So the first one is what's called framing. And what framing means is that on this wire, basically, or on this wireless medium, what's going on is just basically zeros and ones. Okay, it's just zeros and ones all the time. That's all there is. Something has to tell the receiving NIC over here that, okay, this is not just random noise. It's something actually going on. Okay, there's some actual data coming through. How do you do that, right? And the way you do it is that you pick a special symbol. Okay, for example, a symbol sequence like this, 10101010, and you say, okay, this particular byte, which is a special byte, I'm going to repeat it 8 times, okay, one after the other, 8 times. And if you get this sequence 8 times in a row, then everything that comes after that is going to be data, because you expect that there is no data sequence, or noise is not going to have this pattern in it. Okay, so it's almost like you have your sort of your telescope pointed to the sky, and then it's all random zeros and ones. Okay, just random noise, except suddenly you see the sequence, you say, oh yeah, this extraterrestrial intelligence. Okay, that's basically what it is. You're listening to the bits on the wire, it's all random. When you get the sequence, you know that must have been put by the transmitting NIC, and that's the beginning of a frame. So this is the beginning of a frame, and then after that you have the data, and then after that you have the end of the frame. Okay, some other sequence for the end, and this way you know that what's in the middle is what you actually need. And so we can think of this as adding a header to the data, and that is going to be the framing that's provided by the link layer. We need it, of course, otherwise you can't distinguish between noise and data. Any questions on that? Okay, that's pretty straightforward. The second thing is error control. And this is actually a fairly complex topic, and I'm just going to give you the intuitive understanding of what it is. I talked earlier about the header error control in IP, right? I said that you have this parity error control. You kind of choose a bit so that the total number of bits is either odd or even. That's a parity. Parity is just a simplest example of what's called error detection codes, and there are many other detection codes. And I'll give you an example of how one does it. I'll use a error code in, let me just give you an error code that looks like this. So let's say that I do the following. I'm going to give you some number, okay, some integer to be even more precise. And I'm allowed to add to it, okay, so add plus some x. And I want to make sure that this integer plus x is divisible by 7, mod 7 equals 0, okay. So if I give you 3, I'll add 4 to it, it's divisible by 7. If you give me 6, I'll add 1 to it, makes it divisible by 7, right? So what I'm going to send, if you want to send 3, you actually send 3, 4. If you want to send 6, you get 6, 1. If you want to send 14, you send 14, 0. If you want to send 23, you send 23, 5, and so on, okay? As you can see, this is the data. This part over here is the data, right? And this additional information is redundant information. It's extra information. However, what the receiver has to do is to simply check that the total sum is a multiple of 7. If it is, it looks okay, right? If it isn't, then something went wrong. So it detects errors. This is the basic idea behind what's called a checksum, okay, or called a checksum, and it generalizes parity. It's a generalization. In parity, we add just one bit. Here, we're adding a number. In parity, we count the number of ones. Here, we check that the entire number is divisible by something. So the way it actually works is that we take all the bits in the frame, all this data in the frame, and over here, and we interpret this as a large binary number. Okay, this interprets a very large binary number, which it is. Okay, if it's 1,000 bits, it's a 1,000-bit binary number. And to the end of it, we add essentially certain number of bits. We add typically 32 bits, okay, or something like that between, okay, there are many different variations, but let's say we add 32 bits to it, such that the whole thing is a multiple of some number, okay? So this one base. Instead of 7, it could be something else, okay? And so what the receiver does is it takes the whole bit, it divides it out, and if the remainder is 0, it says, yeah, everything is fine. And if it's not 0, it says something is wrong. Okay, that's all it does. And this is what's called the CRC, the cyclic redundancy checksum. And why it works and what, instead of using 7, what number do we actually use? Okay, how many bits do we need for this, and what exactly we do to it is actually very complicated, and it's based on something called group theory, so theoretical part of math. And using group theory, it can be shown that if you choose these things the right way, the probability that you have an error, an undetected error, is very, very small, like 1 in 10 billion. Okay, 1 in 10 to the power 10 is roughly what the errors are. Okay, assuming you have random errors. Any one bit somewhere is corrupted, we can actually detect one error in 10 billion just by adding only 32 bits to it. So this is actually a very important example of how we can use pure math and group theory to come up with something that's actually used in every single NIC today. Okay, so the basis of choosing these checksums and what should be the base over here and what should be the number of bits, etc., is actually based on this mathematical analysis. I'm not going to go into it, but suffice it to say that the idea is exactly this. Take the number, add something to it so that when divided, the remainder is 0. Okay? And if you can do that, then you have good data. Okay? Flow control is really simple at the link layer. And what flow control does is that this link puts out a frame, and the receiver gets it and says, OK, I have it. And then this puts out another frame, and it says, I have it, and so on. So this way, basically, you never have more than one in flight. Okay? And if you do this, you make sure that this NIC has enough capacity. Okay? Okay, and you can do a little bit more. Let's say there's a buffer over here. Then this NIC will keep saying, whenever it's about to overflow, it sends a message back over here saying stop. And when it says stop, it stops. So it's basically never overflows. And because it's just one hop, there's no problem with that, right? It's really straightforward. So flow control at the link layer is really straightforward. Okay. So any questions about flow control at all? Basically saying, look, I can't take it anymore, stop. Okay. And that's it. Okay, so that's the services. There's one more service which is addressing, but I already talked about Ethernet addresses earlier. It's a 6-byte address and so on and so forth. So I'm not going to go into that. When I talk about Ethernet, I'll do that in more detail. Okay, so let's get into this notion of multiple access. And I'm going to set the stage by drawing a picture of a broadcast link. And I'm going to ask these people to pretend to be network interface cards. And so hopefully this will work out. I've never done this before, so you'll find out whether it works or not. So what we have is the following. Let's assume that we have these 4 network interface cards, and these are going to be these 4 volunteers, and they are connected to some kind of hub in the middle, like so. And so any frame that they send out is going to be received by all the others, okay? And that's what we have as a situation. All right, we're going to assume for some of the multiple access protocols that we have some kind of master device, a controller, if you will, okay, which is able to do one of 2 things. It can send a message to the network interface cards, or it can also set up a time base. You can say the time is now 1, time is 2, time is 3, and so on. Okay, those are the 2 things that it could do, and you'll see how we can use it. Okay, so the way we'd like to start off is can the 4 of you kind of face away from each other, and one person is the master. So Heichi, you can be the master. Okay, okay, yeah. All right, the rest of you face away. You can come out. You Heichi, come here. You come here. Ryan, stay there. Stay there. You face this way. Okay, face north. You face that way, this way. Keep your back to Clarence. Right? Okay, that's fine. That's fine. Okay, so the message you're going to speak is very simple. Okay, you're A, Ishwinder, you're B, Clarence, you're C, and Cassandra, you're D. Okay, so you're saying my ID is A, and I have a message for one or the other. Just pick one of the randomly. So A could say my ID is A, my message is for D. Okay. So you can't know when they're about to speak. It's exactly like a network interface card. Okay, they have no idea what anybody else is going to speak. Problems arise when the load is high. When the load is low, when nobody has anything much to say, when you say something, most likely nobody else has anything to say. So the way I would do it is like this. Pick a random number between 1 and 100, okay? And if it's below 5, speak out your message, okay? Not just right now, okay? That would be a low load situation. That would be a 5% probability of any station being active. On the other hand, if you pick a random number between 1 and 100, and if it's below 80, you speak out, that would be a high load. You have 80% chance of being active. If you have a low load situation, essentially every scheme just works because there's nothing else going on, right? It's like you're driving in the city in the middle of the night, nothing is really happening, it's not a big deal. But when you have a busy day, then you have problems, okay? Okay, all right. I know you're facing away from me, it's kind of, okay, let me just start with the first one. So the first way of sharing the air is to actually use what's called frequency division multiplexing. And what that means is that if the 2 women can speak and the 2 men can speak at the same time, their voices are separated in frequency, all right? So go ahead, both of you, just go ahead and start, pick a number and start talking. Let's see what happens.
A, I have a message for C.
Okay, let's increase the load up. So okay, go.
C, I have a message for D.
D, I have a message for B. D, I have a message for D.
You're going to go faster than that.
A, I have a message for
Okay,
A.
that was a collision. Okay. And Clarence, don't turn around. That's not fair, okay? But the thing is, if the 2 of them, if Clarence and Cassandra had both spoken at the same time, it's okay, right? It's because just like your radio stations on the dial, you can tune your FM dial to different frequencies. in the same way they can tune each other out, okay? And that's frequency modulation, okay? Or frequency sharing, frequency division multiplexing as it's called. So we're multiplexing, we're sharing. Multiplexing means sharing. We're sharing using different frequencies, and that's exactly what's going on. So that's the first one, okay? The second one is what's called time division multiplexing. And to show time division multiplexing, H is going to be our time. He's going to be a clock. So he says 1, and we're going to have basically, you go 1, Ryan, you're 1, Ishwin, you're 2, Clarence is 3, and Cassandra is 4. So when you say 1, 2, 3, 4, they each have a chance to speak. Now, they may not speak. Okay, so go ahead.
1, 2, 3.
All right, so we noticed right away that if the time slots are too small, it's a problem. Okay, the time slots have to be long enough for a message to actually happen. So,
Okay. 1,
On A, I have a message for B.
2,
On B, I have a message for D.
3,
On C, I have a message for D.
4.
On D, I have a message for A.
so it could be that they had no message, but you're going to have to waste time. Okay, you'll waste time if you have to, because that's how you get it. It's called time division multiplexing, okay? So you got time division multiplexing. What's going on is that you're sharing in time. In frequency division multiplexing, you allocate a radio station a frequency, for example, and if they don't use it, it's wasted, okay? They go off the air at 11 p.m., that frequency is wasted. Nobody can use it. In time division multiplexing, if you have no message to send, that's wasted. Okay, you can see the difference between time and frequency. Everybody get that? Now we can do something a bit more complicated, which is called code division multiplexing. And in code division multiplexing, each person speaks in a different language. Okay, I hope 2 of you can speak French, 2 of you can speak English. Otherwise, just make it up, okay? So go ahead, just start speaking.
Mi amo A.
All right, Italian, that's great.
I don't know how to say message.
Okay, we'll pause for now and just say, we'll pretend that it works. And so in code division multiplexing, instead of speaking different languages, each NIC is given what's called a code. And it turns out that if these codes are properly chosen, they're what's called, even though we mix the 2 messages, we can actually pull them apart again. Okay, that's a very nice mathematical trick. It's called orthogonal codes or Walsh codes. And we can mix these things. It's just like 2 different languages, okay? And CDMA is actually what cell phones use, right? If you ever got a CDMA phone, that's what they're doing. Each phone is allocated a particular code, and they're using this particular idea of codes. Okay, so those are the 3 ways of sharing the air: frequency, time, and code. But you can do something else, okay? So I'm going to show you a different way of doing things. It's called polling, okay? So polling, we have a master. Now what the master is going to do is going to ask Ryan, he says, A, do you have a message?
A, do you have a message?
You can say yes or no.
No.
No. So you go to B.
B, do you have a message?
Okay. So then B gets a chance to say something, right? So B, so you can sort of say, B, if you have a message, you can speak. And then C, you have a message, you can speak, and so on.
Okay.
So you want to try that?
A, do you have a message?
No.
B, do you have a message? C, do you have a message?
No.
D, do you have a message?
Yes.
D, what is your message?
I have a message for B.
Okay, so that we can stop there. But what's going on is that the master is telling. So A, B, and C had nothing to send. Imagine you had 1,000 stations, 1,000 network interface cards, and only one had a message because it's a low load, right? What's going to happen? It's going to go to each one of them and say, do you have a message? No, 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 no. Finally, one of 1,000 says, yeah, I have a message. You wasted all that time. You're still making sure there's no collision, right? There's no collision guaranteed, but it's wasting time. So that's what happens with polling. But there's a different way of doing polling that doesn't require the master, because let's say he falls sick, okay? He has a software crash, segmentation fault, and he dies, okay? What's going to happen to all the NICs? The NICs are in trouble, right? So they're all sitting there saying, there's no master. Oops, we must be asking somebody else. So what we do is we can get rid of that by having a token. Here's a token. If you hold this, you're allowed to speak. When you're done, give it to the next person.
On A, I have a message for D.
Okay.
On B, I have no message.
On C, I have no message.
On D, I have a message.
Okay, and so this is the way it works, and this is what's called a token ring. Okay, the token is going around in the ring, and when this happens, what's going on is that the person holding the token is going to be able to speak. And again, what happens is you're wasting time. If you have a token, you have nothing to do. And the other problem with the token is you drop it. Now what happens here, 1,000 stations, I don't have the token. Well, somebody must have the token. Well, I don't have it. And so the station management problem is who has the token, and in case it gets lost, what to do about it is so complicated that the technology which was proposed by IBM for many, it was actually started out in Cambridge University called the Cambridge Fast Ring, and then IBM had this token ring protocol. It was very, very expensive, and all the cost was for token management, was to make sure when it get dropped, how do you recover it again? It basically got killed by Ethernet. Okay, so that was token ring. So we looked at two kinds of systems. The token sort of looks like polling, but it's kind of implicit polling, right? It's like the master asking you have permission. Again, guarantees that there's nothing. Okay, now we're going to try something pretty interesting. So you could turn around, and this way I'm going to now tell you. Okay, don't face each other. Yeah. Okay, so here, this one, you're allowed to speak at any time. However, if you have a collision, you're going to have to stop, wait a little bit, and try again. Okay, so anytime you want, you feel like, just do it. Okay.
I'm C, I have a message for A.
I'm B. I have a D. I have a message for A.
I'm B, A, I have a message for D.
Yeah, okay, so there was a collision right there. Okay, and so this protocol is called Aloha. Aloha, which means in Hawaiian means hello and goodbye. Okay, and in Aloha, you're allowed to speak at any time you want, but if you have a collision, you have to repeat it, okay? That's now the problem with the way Aloha was set up was it was on satellites, and you couldn't actually hear the other person, right? But let's say you're speaking and she hears you. She really shouldn't be talking because she can hear you, right? So we'll call that carrier sense, okay? So now what I want you to do is, if you don't hear anybody, you can speak. But if you hear somebody, you should not speak, okay? So go ahead.
I'm A, I have a message for C. I'm C, I have a message for A.
B. I have a message for A. And D. I have a message for D.
I'm C, I have.
Okay, that's good. That was a collision. When you had a collision, what you did was you both stopped. That's called jamming. And then you back off, and then you try again. But what you do is you randomize. You don't start at the same. Let's say your collision, if you both back off for 1 second, you'll collide again, and again, and again. So what you're going to do is when you collide, you're going to kind of mentally count down from a number 7, 6, 5 through 4, 3, 2. Okay, go ahead. Try that. When you collide, back off. Okay, so try that.
D. I have a message for C.
I'm C, I have a message for A.
And D. I have a message for A.
I'm A, I have a message for C. I'm C, I have a message for B.
And D. I have a message for A.
I'm C, I have a message for
Okay, you sort of said, you just started out, right? What happened was that you didn't hear them, just what to start, and so it's almost a collision, right? In real life, there would have been a collision, okay? You would have heard it, it would have been a jam, and you would have both backed off and tried again, okay? And I think that's all I wanted to do. So thank you all, okay? And I'm going to write down everything I did over there, and hopefully you guys get a... So let's just review what we did. So these are all different ways of doing multiple access, and they're all valid, okay? The first one was frequency division multiplexing. And, you know, we network types call it muxing, you know, just to save time. You have time division, multiplexing. Okay, so frequency division means that they're speaking in different frequencies. Time division means the different talks in time, and for this you need a time base, what's called a time base, which means everybody is to agree on the time. That's why we had HE calling out 1, 2, 3, 4 because they all had the same time. Then we had code division, and where they use different codes. So you need to allocate codes. Here you have to allocate frequencies. Okay, then we went into polling. In polling, you're asking each person, and the problem with polling is that if most people have nothing to do, if it's a low load situation, you're wasting time. And if the master were to fail, the network is down, everybody's down. Okay? Then you have token ring or token passing, which is exactly like polling. It has exactly the same problems. It wastes time, And if the token is dropped, it's exactly like having the master go away. So the master disappearing is like having the token dropped, and then you're in trouble. Okay? And then we have Aloha, where basically it's what I call the Nike protocol. Just do it. Okay? It's called, and if the load is low, it works fine. Okay? It's like saying on a traffic intersection, the place where the roads intersect is a multiple access point. Okay? Right? It's a multiple access point. So if two cars decide to be in that point at the same time, you have a collision, right? A real collision. Aloha says there are no traffic lights anywhere. There are no stop signs anywhere. If you have a collision, you die, you get reincarnated, and you try again. No big deal, right? For people, it's a problem. For packets, it's no problem. They get reincarnated all the time. Drop it, just retransmit it. No big deal. So Aloha is the reincarnation protocol. So you just go through. There's no traffic lights, no signals, nothing. Just go. Okay. Then we have CSMA. CSMA stands for Carrier Sense Multiple Access. Probably should write it out. And Carrier Sense Multiple Access says this. Let's listen first. If somebody is transmitting right now, we ought not to transmit, right? That makes sense, right? And if we aren't transmitting, if nobody is transmitting right now, let me go ahead. But there is still some chance that two people start at the same time, or almost the same time, in which case you will have a collision. What you do then is you have CSMA with CD, collision detect. This is CSMA plus collision detect. And what this means is that we are going to listen. If we hear nobody, we can start. And if what we hear is not what we said, if what we hear is not what we said, it's because somebody else started speaking at the same time. That means we have a collision, in which case we both stop, back off, and try again. And we can't back off the same amount of time. We're going to have to back off random amounts of time, okay, and try again. And that's called CSMA CD, Carrier Sense Multiple Access Collision Detect. And this has collision detection plus it has a random back off. And this, in fact, is what's used by Ethernet. Okay, so CSMA CD is exactly what's implemented in every single Ethernet network interface card today. And so we have this notion of a carrier, which is anything happening? And if there isn't anything happening, we're allowed to, the NIC is allowed to transmit. And it has the ability to detect collisions and send this signal called a jam signal. So everybody knows there's been a collision. And then the stations that collided back off randomly, try again. What happens if they collide again? What they do is they double the back off. So how do they do that? It's like this. So if there's a collision, okay, we choose what's called the back off value. Randomly in the range 1 to sort of max, or actually 1 to, okay. And what we do is that we set back off equals twice back off. We back off down. Okay, and then try again. Okay, if collision, we go back over here. Oops. If sorry, I already wrote if collision. Try again, which means you go back over here. Okay, and if there's no collision, you're fine. So what's happening is a collision. We choose the back off value randomly in the range. So we start off with back off equal to some small value, like equal to some initial value. Something like, few hundred milliseconds, as it turns out. So you have some initial value, there's a collision. If there's no collision, life is good. You got through. If there is a collision, we choose the back off value in the range Okay, 1, 2, okay, maybe I should. I choose a back-off value randomly in this range. Okay, I double it, I count down, back-off value. Okay, and then I send the packet. So, for example, if two collided and the initial back-off value was 10, they'd both choose a number randomly in the range 1 to 10. One may choose 6, one may choose 2. So you start counting down. 2 goes to 1, 6 goes to 5, 1 goes to 0, 5 goes to 4. Okay, the person who counted out to 0 wins. They're going to try. They got through because the other person is going to be still at 4, right? Let's say they both chose small values, they both counted on, and they both got to 0 at the same time. They're going to double the range and try again. Hopefully they won't collide again. So far, so we went through 1, 2, 3, 4, 5, 6, 7, 8 different multiple access schemes. And pretty much all of them are used today. So frequency division multiplexing is actually used for cell phones. And source time, they combine together. So you have frequency allocation, and then in the frequencies, you allocate time slots, and that's how GSM works, okay? Or anybody using a Rogers cell phone, they have actually at the bottom of it, you have frequency division multiplexing. There are 20 different frequencies, and each frequency is divided into 8 time slots. So you get 8 different time slots, and each station or each cell phone is given one of 8 different time slots, and that's how that works. Code division multiplexing is a competitor. That's all the Qualcomm phones, all the Bell telephones are using code division multiplexing. Polling is, and token passing have kind of fallen out of favor, but they were being used in the past. Aloha is used in satellite networks, so anybody using a cable modem at home, okay, they're actually using Aloha. They're using a variant of Aloha, but it's basically Aloha. So all cable modems use Aloha actually. And then CSMA CD or CSMA, the pure CSMA is not really used, but CSMA CD is what's used in Ethernet. So all of these are used, and these are all basically link layer multiple access protocols. What is Ethernet? So Ethernet actually now has become a brand, okay? What started out in the early 70s as being this coaxial cable, okay, to which workstations are attached, you know, like the, so maybe I'm not drawing this properly. Okay, so let's see. So here's your mini computer, and that was a network interface card, and then you had this tap over here, you had this other tap, and another mini computer. So the way we would represent it today would be like this. We would call it essentially like a special term for it. It's called a bus. Okay, so we have a bus, and on the bus we have these taps, and we have these different nodes. And so the Ethernet cables used to be these thick yellow cables. I don't know if you can actually see them in DC if you look around for them. They're about this fat, and they're always bright yellow because you had to find them. I'll tell you why in a moment, but they kind of wind around like this, and you'd have these stations kind of screwed into them. It was fine, except there was a problem. The problem was that if for any reason this cable got cut or bent or twisted or something, it was very hard to determine where it went wrong, where the problem was, right? So you would be connected, this node is connected to here. Let's say this was connected through some router into the internet, right? This was a router over here. And so all of these were getting access to the router in this way. Okay, maybe I should draw it properly. It's like this. The router had if this was cut over here, these nodes suddenly would lose internet access. So they would call the IT people and say, hey, we lost internet access. And I'd say, oh, okay, maybe your cable is damaged. But where is the cable? It's somewhere up there, right? So you take a flashlight and kind of go around and find, you know, whether some mouse or squirrel or something, you know, chewed through a cable. Okay, and it was really a painful thing. That's why they're bright yellow, so you can locate them and fish them out and fix them up. And they continue to do that. So this kind of didn't really work. It isn't easy to diagnose. It isn't easy to debug, and so on. So while it worked, it wasn't very. It was quite successful. It wasn't really scalable and, you know, maintainable and so on. So it changed, and the way it changed was that instead of having a bus like this, we can take the same exact picture. Let me just label these systems as A, B, C, D, E, and then the router. Let me draw the same picture slightly differently, and you'll see what I'm doing here. So I have A over here. Okay. So that's R, and then it's B, C, D, E. Okay. So this line is actually the same bus over there. Okay, except that I kind of make it go through this central point each time. Okay? And if I do this, then this becomes a place where all these are going to come over here. So for some reason, let's say that this node says I'm down, okay, as a break over there. What you do is you just patch over it, and everybody else is fine. Then you can go find out what's wrong with that later. Okay? So just by running this wire in this fashion, you're able to make it much easier to build it. And it was not too much later to discover that instead of doing this, why don't we just have a hub, like I showed earlier, where all of these double wires are replaced with single wires, and you just go like that, and you just put a router over here. All we do is internally, we just have electrical connections so that no matter what's sent on either one, gets sent on all of the others. Excuse me. Okay, so that's the basis for hubs. So they're easy to maintain, it's certainly scale out, and you don't need the bus anymore. You don't need to go fishing for anything going wrong. So for example, if this connection from here to there were to break, then nobody else is affected because they have their own separate electrical connection as opposed to having a bus. And that's what people use today. So this has become completely standard. Nobody uses the bus type configuration anymore. Okay. Any questions on that? Okay. So that's sort of the evolution. The other thing that's happened is that we've gone from 1 megabit per second in the beginning to 10 megabits per second. And I think that's gone up to 100 megabits per second. So you can, typically what you use at home would be the 100 megabits per second. You can also get 1 gigabit per second and 10G, and there's 40 gigabits per second standards on the way. So data centers use 10G all the time, and of course the standard like on desktops today is 1G, right? 1 gigabit per second. So 1 gigabit per second is 1,000 times faster than 1 megabit per second, all right? So we've got a speed of 1,000 increase in the last 30 years or so. This is pretty good. The other thing that's happened is that these things have gone from copper, which was the original, to fiber in many cases, optical fiber. And by using optical fiber, you can get much faster. And the other thing that's happened, and I'll stop with this last thing, is that instead of having just this hub-like structure, we instead have these network interface cards with a little bit of memory or a buffer, as I've shown over here, showing like a stack of plates, as you'd see in a stack, in a cafeteria, stack of packets. And the reason why this helps is that now, let's say you send a packet from here, and this is also sending at the same time. You don't have a collision anymore, right? Because they both just get sent over here, then you figure out where it goes, and you send it out over here or there, etc. And so this becomes a switch. Okay, it's not a hub anymore, it's a switch. And that becomes an Ethernet switch. So if you have an Ethernet switch, do you need CSMA? You don't, right? You don't need it at all. So the original Ethernet, which started out by saying I'm going to take a bus and I'm going to have Aloha and CSMA, CD and all that good stuff. If you use hubs, you still need it, but if you use switches, actually you don't need it anymore. And as memory gets cheaper and cheaper, there's practically no reason why you still need to use hubs anymore. You can actually get an Ethernet switch, throw a few kilobytes of RAM, a few megabytes of RAM, if you will. And so we actually have solved the multiple access problem by converting broadcast links back into point-to-point links, which is really what we've done. So if you started out this lecture saying, if it's point-to-point, it's no big deal. And so Ethernet, which started out as multiple access, it's cheap, no need for memory, no need for coordination, no need for master, no need for tokens, became faster, went to hubs, and now we're in the stage where pretty much everything is Ethernet switch, so that multiple access problem has kind of gone away. But it's reappeared in other places. It's reappeared certainly in cable modems and other areas in the cell phone network, for example. But in Ethernet, it's kind of gone away. So when you talk about an Ethernet switch today, there's no CSMA CD. You can turn it off. It's not going to make a difference. But for hubs, it will make a difference. And at homes today, just because they're cost sensitive, people pretty much will use hubs. But everything in corporate world, in university, for example, is all Ethernet switches. Okay, so I'm going to spend the last little bit talking about the Ethernet frame itself. And it's useful, as I said before, it's always useful to look at the header, because it tells you exactly what the protocol is capable of doing. We did that for the IP header. So I'm going to show you the Ethernet frame header. And so this is what it looks like. So we first start with the preamble. And the preamble is what tells you that there is going to be actual packets after this. And this is 7 times this sequence, 10, 10, 10, 10. So you repeat it 7 times, and that says, OK, what follows is actual data. And the 8th byte, we have one more byte. It's called the start of frame. Start of frame. The start of frame is 10, 10, 10, 10, 11. Okay, and now we know we have data. What is the data? Well, we have a MAC destination, so we need the destination address, and this is 6 bytes. And if you remember, the 6 bytes are 3 bytes for the manufacturer ID, and then 3 bytes is the serial number. And these are not aggregatable, but they're globally unique, right? Everybody in the world, every NIC in the world has its own MAC address, but these are not aggregable. So your destination address, and we have a source address. As you can imagine, it's also 6 bytes. And then we have this, we have what's called a type field, and we basically, this is just to maintain backward compatibility, because there's, okay, so we, actually take it back. So the type has got, it's got 2 parts to it. What kind of Ethernet, because there are many variants of Ethernet. And the other one is, what's the upper layer protocol? In this case, the network layer protocol. So Ethernet can be used to carry not just IP, but other protocols as well. So in the days that Ethernet was invented, there were other network layer protocols. There was Digital's own protocol. There was something called XNS, which stands for Xerox Network Services. DNA was Digital Network Architecture. And then Apple had AppleTalk. And there was other companies which had their own proprietary network layer protocols. So this type field would tell the NIC which protocol to hand it to. Should I give it to XNS? Should I give it to DNA? Should I give it to IP? Whatever. So that's over there. We always need that. And then we have the payload. And that's what the data is inside. And for it actually, in our case, it consists of the IP header, the TCP header, and then the data over here. So that's all encapsulated into the Ethernet frame. And then following this is the CRC. This is a 32-bit cyclic redundancy checksum. And that's basically it. That's the frame, right? So we have a trailer. Now you might say, why is this in the trailer? Why is it not in the header? And the reason is because in the hardware, what happens is that as the frame goes through, we can compute the sum that we want, and then as it's just about to leave, we stick the last little bit to it to make it so that it's divisible by the appropriate number, and that gives you the CRC. So it was easier to implement in hardware, so we stuck it into the trailer rather than the header, but conceptually it belongs, along with the metadata. Okay, and so this, by the way, is from Wikipedia. I just cut and paste this. I just printed it out from Wikipedia. And so if you go to Wikipedia and look at it, you'll now understand exactly what Ethernet does. Okay, there's nothing here that I've left out. There's one optional tag which I left out, which is not really relevant, but that's optional. So you now understand enough about Ethernet to actually know exactly how to go read the exact protocol spec.